Welcome everybody to the second day of the summary meeting of the first session, the first half of the ARA meeting. At the start of the Zoom session, I'm asked to remind you that the meeting is being recorded and live streamed. If you don't wish to be recorded, you need to keep your microphone and camera off and use the chat button for any questions. A live transcript will be active, but you can turn this on and off through clicking on the live transcript button at the bottom of the Zoom screen. Okay, so I'm really pleased to welcome today Chris Lustri, who's going to give a talk. So Chris studied for his BEng BApp Sci degree at QUT, and he first came into contact with exponential asymptotics when he took a master's project with Scott McHugh. In 2009, after graduating, he moved to study for DPhil at Oxford with John Chapman. And on graduating from that, he moved back to Australia to work with Nalini Joshi in Sydney on discrete integral systems and the asymptotics of those, including Pan-LaVey. Since 2016, he's been a lecturer, senior lecturer, and now I believe head of applied maths at Macquarie University. Chris is an excellent host, and he's got incredibly broad mathematical interests, and that's led to many interesting collaborations that he's carried out and stimulating discussions and research outputs along the way. But today he's going to focus on applications of exponential asymptotics to 3D water waves and partial chains, and the title of his talk is Submarines and Particle Chains, Some Interesting Applications of Exponential Asymptotics. Over to you, Chris.
Thanks very much for that introduction. It was very kind. This is a picture of one of my favorite particle chains. I think it's very appropriate to see Newton's cradle given the venue of the talk, but let's get into it. So I'm going to talk about water waves, and I'm going to talk about particle chains, and both of these have been covered or touched on in various different talks throughout the meeting, and I'm going to highlight that when that's appropriate. So at the top two pictures, you can see two images that I grabbed off Wikipedia. One is the waves forming behind a duck, but another one is waves forming in the atmosphere as the wind goes past a mountain. When we talk about waves in flow, we don't always mean fluids. So while that's what I'm going to talk about today, I want you to keep in the back of your mind, I don't just mean water waves, although that's the main emphasis of this talk. Down below, I'm talking about what I mean by a granular chain, which is kind of a chain of particles that are touching each other and sending energy throughout. And here's some pictures of some applications that you can follow up on if you're interested. What I want to do in this talk is actually oriented around answering 4 questions. And some of these questions have been touched upon, some you'll be seeing here for the first time. The first is, do submarines create a Kelvin wedge? And I'll talk a bit more about what that means soon. The second is, when you have an unsteady fluid dynamic system, what is the role played by higher order Stokes curves? Now, I almost never get to talk about this, so I'm really excited to answer that particular question. Then I'm going to move on to granular chains. I'm going to talk about what causes a phenomenon known as anti-resonance conditions. And we've seen a few problems like this already in the Newton program, and it might not surprise you when you see the answer. And I'm also going to talk about what is an open question that we've made some progress on, which is what happens when we don't have leading order solutions that we can just write down. I apologize for my voice. I'm not feeling particularly well. My voice might struggle a little bit, but I'll try and keep it together. Normally, when I give this talk, I have to spend about 20 minutes explaining what exponential smallness is, what Stokes lines are, what exponential asymptotics is, but we've all just sat through a program where a lot of people did this really, really effectively. So instead, I'm going to compress it down to 3 slides and follow a very abridged approach of the introduction, which will tell you everything you need to know, but I will leave the details for the talks in which they were given. So the first thing I want to talk about is Stokes phenomenon and the critical things you need to know. Stokes phenomenon is caused by exponentially small terms which switch as we cross curves known as Stokes curves. Now, when I say exponentially small terms, what I mean is there's 2 contributions and one is exponentially smaller than the other. This isn't an absolute statement, it's a relative statement. The second thing is, and this highlighted again as a relative statement, there are other curves known as anti-Stokes curves. And that's when you've got two different exponential contributions that change their relative size. One was exponentially smaller, it switches to become exponentially larger. And finally, the other critical thing you need to know is algebraic series on their own can't see exponentially small terms. So you need to do something a bit smart. I tried to find some interesting facts about Stokes County, North Carolina, and discovered that it seems to be one of the most boring places in the world. I apologize if you're from there. I couldn't really find anything interesting to add to the picture. So the second thing you need to know, what are we going to do? Well, we're going to calculate the algebraic series anyway. And what we're going to do after that, if you want more details, you should see the talk that John Chapman gave very early in this program, where he talks in a lot more detail about this method developed by Chapman, King, and Adams. And the idea is the series terms are eventually dominated by repeatedly differentiated singularities. Even though you might not be able to get the second or third term in the series, you can make a really good guess at what the terms look like eventually. So knowing this, we choose an ansatz for the late order terms. And the ansatz follows this very familiar factorial over power form. Now, how we do this and how we figure it out, I'm kind of going to leave out of this talk. The mechanics is something that some of the other talks have looked at a bit more carefully. What I want to draw on is this term on the denominator, this chi term, which is called the singulant. Now, the singulant kind of carries the information about these singularities. It's set to be 0 at the singular points of the leading order, or if we're being pedantic, other early order terms. So this singulant is very, very important because it carries this information about the leading order into the later order terms. It's also very important because it tells you what your exponentially small terms look like. So if you know what the singulant is, then you can see by this form, the exponentially small remainder, the thing that switches on when you cross a Stokes line, is this equation we have at the top. Some Stokes multiplier that jumps as the Stokes line is crossed, times by a prefactor that we're not going to care about at all in this talk, times by this exponential. And you can see that the singulant appears in the exponent of the exponential, which means that it plays the biggest role in controlling how big or how small our terms are. Once you know the singulant, you know about all of your exponential scales. Furthermore, once you know the singulant, you know where all of the Stokes lines and anti-Stokes lines are because they satisfy this very simple condition I've written at the bottom. If I have two contributions and each has a different singulant, then the Stokes switching between those two contributions occurs where their imaginary part is the same. And the term that switches is the one which has the greater real part because we can see by the form of the exponential that one is going to be exponentially small compared to the other. That's it. That is the crash course introduction to Stokes phenomenon. It's everything you need to know. If you want more details, there've been a lot of really interesting talks where they can delve into why this happens, how it happens smoothly, all of the things that we've seen, but we're focusing on applications today. So let's talk about the first application that I named, possibly somewhat exaggeratedly, submarines. There's nothing to say this couldn't be a submarine, but in the interest of keeping the math fairly simple and tractable, we're going to make it a point source, which is a very simple submarine, I guess, if you want to squint and turn your head and change the singularity a bit. So the setup is this. We have some background flow flowing over a point source, and we want to know the position of this free surface Z. And what we want to see in particular is what waves form as the flow cruises past the source. What are the surface waves? Now, it's an asymptotic problem. We want some small parameter. The small parameter we choose here is the Froude number, which considers the ratio of inertial forces to gravitational forces. And what this means fundamentally is the flow is kind of slow. So it's inviscid, but the flow is still not going particularly fast. Now, a much more detailed exploration of this was given in Scott McHugh's talk a couple of weeks ago in the Applied Math Theme Week. So what I'm going to do for the next few slides is kind of recapping the setup, which may seem quite familiar, but we're going to go into some interesting directions. So this is the physical picture. Let's do some maths because that's what we're all here for. The governing equation for inviscid flow, we're going to say is Laplace's equation. We're going to have two boundary conditions on the unknown free surface. So we don't know where the free surface is, but we know on the free surface, we have these two equations. The first boundary condition says that there's no flow through the surface. The flow is steady, the surface is fixed, it's staying in the same place. The second is the Bernoulli equation, which tells us that the pressure is balanced at the free surface. And that one gives us a lot of our interesting behavior because we can see straight away, remember we said the Froude number is small. Well, that has a Froude number multiplied by the gradient of phi. So that is a singularly perturbed condition. We're also going to say that the submerged source kind of looks like this thing that I've written down there. That basically says the source has strength delta. So when I say strength, I basically mean the amount of stuff that is being produced by the source. Okay, so this is a fairly kind of idealized setup. Obviously, a submarine looks a little more complicated, but it gives us some idea of what the math is going to do. However, we want to make it even simpler because it turns out we still don't know where the boundary is, and that makes life a little bit difficult. So we're going to say that the source is very, very weak. Delta is small even compared to the Froude number. And that allows us to linearize, meaning we can deal with a linear system, which is easier than a nonlinear system. So we linearize the equations around the undisturbed flow, which is to say phi looks like x plus some small parameter, plus some small variation, and the free surface is 0 plus some small variation. So the linearized governing equation doesn't change because Laplace's equation is linear, but you'll see now that z is between minus infinity and 0. So now we have a fixed boundary and that's fine. Our boundary conditions become linear. It's still singularly perturbed. And also all of the usual stuff happens with the source condition and far field conditions fine. So now we're going to do exactly what I said before, and I'm glossing over this quite quickly because this is not really about the nitty-gritty of the analysis. So like I said before, we find an algebraic series. We know it's not going to give us our answer, but we know it's an important step towards our answer. So we define a series for phi in terms of our small parameter f. And then we work out the equations for the series terms, which are given on this slide. The actual thing I want to draw your attention to is the leading order equation, so phi naught, because this tells us where those singularities are. Now we're going to look at the complexified free surface. So we're going to look at what's going on at z equals 0, and we can see that this leading order is going to be singular at x squared plus y squared plus h squared is equal to 0. Now, there's no real values of x and y that satisfy that, but there's absolutely complex values, so we're looking pretty good. I apply my late order ansatz, where I'm treating x and y as complex variables, and then with a little bit of work, I can find my equation for the singular, which, as I mentioned, tells us everything we need to know for the purposes of this part of the talk. So we set chi to be 0 on the point I mentioned before, x squared plus y squared plus h squared is 0. So this says that the zeros in the singularities in the leading order are going to propagate through to the late orders. And it gives us this nonlinear first order PDE, which we've got down the bottom. And you can solve that exactly. It's fun. It's a nice exercise. Everyone should do it once in their life. And you can actually get out these values of chi. And it turns out there are 4 kind of true values of chi and 4 spurious ones that came about because I took a squared at some point in the analysis. So there are essentially 4 chi contributions which occur as 2 complex conjugate pairs. They give me 2 kinds of waves. Once I know chi, I can write down the form, which I've done at the bottom, but this is all just kind of algebra. It makes more sense for us to look at what's actually happening. So you can see that there are essentially 2 kinds of waves that switch on. The first are these transverse waves, which I have on the left, and they appear across a Stokes line, which follows the line x equals 0. So even though the waves seem to be restricted to a wedge, there are actually exponentially subdominant waves outside that, but then very, very small, and you can't really see them on any picture. So those are there, and they appear because of the algebraic series. But the second contribution, the divergent wave, occurs when the divergent waves are switched on by the transverse waves at this point where their imaginary parts of the singulants are equal. And it turns out that they are restricted to a region which, the further you get away from the source, the more it looks like the Kelvin wedge. So it's not precisely the Kelvin wedge in the same way that you see using stationary phase analysis on a surface ship. Here it's a little bit more complicated, but you do see the same behavior. So you run some simulations, and what you see is something that looks like this. And this makes sense. We expect the transverse waves to be the visible ones because they are exponentially dominant even compared to the divergent waves, this sort of feathering on the side. And that's not what you see in a ship. What you see on those ducks or those clouds that I saw is you see a lot of feathering on the edge of the Kelvin wedge, which is the divergent waves. But as soon as you go below the surface, that becomes exponentially subdominant and much harder to see. Now that's kind of, from an applied perspective, almost the end of the story for this part, but there's a really nice thing from a complex analysis perspective, which is when you actually leave the real axis. So here what I've taken is a cut for constant x equals 1. So I've taken a slice top to bottom, and then I've looked at what happens when y is permitted to become imaginary. So this is constant fixed x, complex y. And all of a sudden, this weird kind of pattern that we saw here makes a lot more sense. Okay, this doesn't look obvious. But here you can see there are actually 4 airy singularities sitting off the real axis, 2 above and 2 below. And those airy singularities tell us where the Stokes curves come from, and the anti-Stokes curves, which just reflect a change in dominance between the transverse and divergent waves. Now let's take a closer look at the top right-hand corner one. And we can see immediately which sections possess which waves. So if we start at the branch cut and then go clockwise, that first region contains only the transverse waves. We then cross over the second Stokes, over a Stokes line, the black curve, into a region where the transverse waves switch on the divergent waves, and they're both present. We cross the anti-Stokes line as we go up, so now the divergent waves dominate the transverse waves, so that when we cross the top Stokes line, the transverse waves switch off. And we get this kind of pattern that we learned, that we recognize is exactly the same pattern as the airy function. These are airies sitting off the real axis, which is powering what's going on. So that's very nice. And to kind of wrap this up, you can do other problems. So this is what you have when, instead of small Froude number, you neglect gravity and consider surface tension. Now, that's a very, very different scaling. You're looking at very small scales. That is not the world's largest ship-sized bug. That's just a bug. But you can see kind of the same thing, except now the waves extend ahead of the obstacle rather than behind. This is something you do see quite often in surface tension waves and capillary waves. So what's left? What I'm doing at the moment, one of the things I'm doing at the moment is looking at gravity capillary waves. What happens when you have both? And it turns out when you have both, you can write down the singulant equation, as I've done here. It's a lot more complicated to solve. I was hoping to have some pictures, but the divergent waves are very difficult to calculate this way. But one thing that's interesting is going back to this, because what you see here versus what you see in capillary waves is extremely different. In capillary waves, 2 of these singularities kind of disappear, or at least go somewhere irrelevant. And I'm really interested in sort of unpacking how that happens. So that transition as the capillariness is turned on is very interesting. Some other things that are kind of still being done in this, in addition to some of the stuff I've done, I'd like to refer you to Janus Johnson-Lambius's discussion session where he talked about nonlinear problems and internal waves. Here I just quickly sketched out what happens when you have an elastic boundary condition, which is surface ice. And it turns out it kind of looks like capillary waves. It's actually a little friendlier, but to be honest, those waves decay so fast that it's kind of hard to know what to do with this information. I hope I can publish it at some point, but I don't know, it probably needs a little bit of thought. But the other thing, and this is kind of interesting, is I've been talking to an oceanographer and a data scientist over at UNSW who said, this is nice, but can you see it? And I was like, I don't know, I guess we should figure this out. So we've got this project and we're actually looking at doing it sort of in conjunction with an industry partner, and we have funding for it, by the way. So if you know any PhD students who want to do this and sort of take a more industry friendly stance, give them a heads up. And the idea is, what if we put on realistic ocean noise and then apply data science type techniques to try and retrieve these waves, given that we kind of know what they look like? And here's an incredibly simplistic example. So not ocean noise, not data science. I've just said, well, if I have the wave and I throw on white noise that has 10 times the amplitude, and then we just calculate the autocorrelation, you can see that the wave signature kind of falls out really nicely. So the question here is, can we do this with more realistic noise? Can we do this with more realistic shapes? Can we do this with more sophisticated techniques for pulling out the footprint? But that's all I want to say about steady flow. What I want to talk about here is unsteady flow. And I never get to talk about this because this takes us into higher order Stokes phenomenon, and that's a very complicated idea. And there's probably like 10 people in the world who really care about what I'm going to say, but I think they might all be in the audience, so you can all sit through it. The setup is basically the same, except now our linearized boundary condition has time variation. So our singulant equation, slightly more complicated. It has this chi-t term in the fourth power, but actually not that much more difficult to solve. And what you find when you do is that instead of the two kinds of waves we saw, you get a third effect. And that's a transient ripple, which propagates downstream. So the source is basically where that wave peak is, and we've got this expanding ripple that is just drifting off behind the wave. That's the transient effect, and that's what kicks everything off. So the unsteady ripple switches on the transverse waves. That's the first domino. And that is at the point where the imaginary part of the singulant for the unsteady waves is equal to the imaginary part of the singulant for the transverse waves, which happens across this line you can see here. So I've drawn it, and I've drawn some arrows to show you where it's going. So as a primer, what happens here, sorry, I've lost my mouse. That's okay, I will just gesture. So what happens here is that Stokes line at the front, when nothing seems to happen, is because on that Stokes line, the transverse waves would dominate the unsteady ripple. But since the transverse waves aren't there, nothing happens. Then that dotted line is an anti-Stokes line. So behind it, the unsteady ripple dominates the transverse waves and they get switched on. So you've got this expanding blue region full of waves. But this doesn't tell us where the divergent waves come from. That's a much more complicated question. There's a lot more things to consider because the unsteady waves can interact with the divergent waves, and the transverse waves can interact with the divergent waves. And it turns out if you draw all of these, even given the fact that that Stokes line on the right must be inactive, and I've included that for a reason, so file that one away, this picture doesn't quite make sense. There's no way you can construct this such that the wave region is bounded. And that's a problem because the wave region has to be bounded. It doesn't make sense because we're missing something. And if you know what you're looking for, you'll immediately identify that there are 3 contributions in play here. And if you were watching Chris Howe's talk earlier in the program, you'll know what that means. Because as soon as you have 3 contributions, you have higher order Stokes curves, which are another thing entirely. Higher order Stokes curves are curves across which Stokes curves themselves switch on and off. They are fascinating. They're kind of like the next step up in a more complicated Stokes hierarchy. And they follow curves where you see this interaction between 3 exponentials in this way. So the imaginary part of the difference between the 2 is equal to 0. It doesn't matter which one is 1 and 2 and 3, that permutation holds. So we want that thing to equal 0. Where are they born? Because we know Stokes lines come from singularities. Well, higher order Stokes lines come from Stokes crossing points, points where all 3 Stokes lines intersect, and we have 2 of those. So there is some higher order Stokes phenomenon going. So knowing that, and I've skipped out some of the messier pictures with a lot of different things going on, but I've boiled it down to this, which has all the interesting information. So we have this divergent wave region, and we know at that Stokes crossing points, it turns out that these Stokes lines, the blue and the red one, have to terminate. But even with just that information, it's not clear which one of these 2 cases is true. there's two things that could happen. Either both curves terminate to the right and we get this kind of narrow wing-shaped wave region, or one terminates to the right and one terminates to the left and we get this kind of bulbous expanding triangle. But there's no way to tell which one is correct if we restrict our attention to the real free surface. Now I'm going to show you a picture that tells you the answer, but this picture took me a very long time to find, and I had a whiteboard full of different cuts of this four-dimensional complex plane and strings, and it looked like something out of that meme or A Beautiful Mind or whatever you like. Lots of string, lots of paper, and I was eventually able to pull out this picture. So this picture is real value of x, imaginary value of y. So I fixed the real value of y at a non-zero value, and I fixed the imaginary part of x being 0. So you can think of this as being perpendicular to the picture we're seeing here in a cut this way. So the actual Stokes line is these dots at x equals 0. That's where these Stokes lines are intersecting the real free surface. Those are the things we're seeing. So you can see immediately there's 3 places where the blue curve intersects the free surface. There's this one on the left and there's these 2 on the right. If it was active on the right, then both of these dots would have to be valid. Both of these dots would have to be active. But those dots actually correspond to the 2 Stokes lines on the right-hand side of this picture. And we know the Stokes line furthest to the right can't be active. So this actually tells us that we can't have them separate. You either get neither of them or you get both of them. Neither of those are options. Sorry, well, 0 of them is an option. You can't just get one of them. So in fact, this Stokes line has to terminate at the 2 Stokes crossing points from the left. This is a really sort of complicated idea that took a lot of figuring out. It was the one time in my life I've wished I'd known more about elliptic curves, but that feeling drifted away pretty quickly. But you can see that without the higher order Stokes line, without knowing that this Stokes curve terminates at the Stokes crossing points, we couldn't really come up with an accurate picture of what was going on. So what did the higher order Stokes phenomenon do? It told us what the wave region was. It tells us how these waves appear and how they evolve. But without the higher order Stokes phenomenon, we could never have drawn this picture. Now that's all I want to say about fluid flow. There's a lot more information in the relevant papers where we validate it numerically and do all of that fun stuff. But what the point I want to kind of bring home here is the minute you have more than 2 contributions, you have to start looking for much more subtle Stokes phenomenon effects if you want to really understand what's going on. So, particle chains. Doug Wright gave a really nice introduction to the idea of particle chains. I would like to show you my favorite. Thank you, Guo, for letting me borrow your Newton's cradle. This is a particle chain. What happens is you have some beads and they're touching each other. And I put an impulse in one end and it propagates through the beads out to the final one. So this is a very common kind of problem. Some of you may remember that the Fermi-Pastor-Ulam Singu system was the first place that people really started to get a handle on the universality of solitons. So we're thinking of it as a chain of particles with constant mass is the monoatomic version. A chain of particles with alternating masses is the diatomic version. And there's some kind of interaction effect, which I just call an F here. And I'm going to look at a few different Fs and talk about how our method is going to evolve. Now, if the mass ratio is small, if one set of masses is much, much heavier than the others, then this is a singularly perturbed problem because you've got this epsilon pre-multiplying the second derivative in Z. So we've got this singularly perturbed system. If the masses are incredibly light, you can kind of see how this is perturbed around a heavy monoatomic system. So I was drawn to this by some experiments that Mason Porter showed me, which showed that if you have these diatomic chains, you get these trailing ripples behind the solitary wave solution. So monoatomic waves often support solitary waves, exponentially localized, traveling without decay or attenuation. In diatomic chains, not necessarily true. Instead, you get these tiny little ripples that suck energy out of the main pulse, which is a problem because you want that pulse to have all of the energy. So what they want is to understand where these ripples come from, why there seem to be some configurations that they disappear, and how they can be avoided. So let's jump straight in and come up with the nicest possible particle chain we can. And this is the total lattice. The total lattice, I think a large portion of people watching this will immediately say that's integrable. You're cheating, that's much easier. And you're right. The total lattice is almost a cheat. It's an integrable system. The monoatomic system can be solved exactly, which allows us to write down an exact leading order solution, but that's great because leading order solutions tell us where all the singularities are, and we can treat that as telling us what singularities have to propagate into the late order terms. So I've got this diatomic lattice. I'm saying Y is the heavy particles, Z is the light particles, and I get this leading order solution, which is a bunch of logs. We play the same game we always play. We find some late order terms, I've called them Y and Z, and we calculate the singulant. The singulant depends on the leading order, but that's fine because we know the leading order. So we do all of the exponential asymptotics, that is excellent, and we get an expression for, and I've written down the oscillatory behavior of the light particles. You can do the heavy ones, but the light ones are just a little more easy to write down. And you can see there's these two exponential contributions. And these exponential contributions come from different singularities in the leading order. So this is all algebra. This is what we actually see. So Xi being real corresponds to the real wave propagating through. So all of the singularities, which I've labeled here as dark circles, are off the real axis. And you can see the critical thing, ignore the anti-Stokes curves, they're not particularly relevant to this problem. The Stokes curves intersect the free surface. There are two pairs. There's the pair on the left. So ahead of the wave, which is the far left, there's no contribution. And as we move to the right, we cross the first dashed curve, which is a Stokes curve, into the region containing the origin, which is shaded light blue. This has one exponential contribution, well, one pair. And then you keep going to the tail of the solitary wave, and you can see that we cross a second Stokes curve into the dark blue region. So now we've got both sets of oscillations going on. So if we just sketch out the oscillations, it looks like this. So region 1 is ahead of the curve. Region 2 is kind of where the curve, ahead of the traveling wave. Region 2 is where the traveling wave is, and region 3 is the tail behind the traveling wave. So you can see those exponentially small things we saw in the experiment are actually exponentially small contributions switching on across Stokes curves in the complex plane, which is pretty cool. It's totus, so it's not a real physical system, but we'd like to get to that. So we put it all together. We've done the math. We've got our algebraic series. We've got our exponentially small terms. We can even relate chi2 to chi1, which is going to be really helpful in a moment. Even though it looks hideous, it turns out you can evaluate that. It's 2 pi I. So chi2 is equal to chi1 plus 2 pi I, which, I mean, Mathematica did it first and it took some validating, but it's true. And that's really nice because the oscillatory term cancels entirely if this very simple condition holds. If the mass ratio is equal to 1 on m squared, where m isn't any integer. It seemed too simple. It seemed too nice, but we may as well compare it with some exact solutions. So what's happening here is you've got one Stokes contribution switching on. You've got a second contribution switching on, but it's cancelling entirely. Now, there's a lot of physicists here who do quantization. This is not a surprise, I suspect, to you. This is something you're like, yes, obviously. It was a surprise at the time. This is a quantization type thing, except the solutions where the quantization effect doesn't happen are still physically relevant and interesting. So if you compare the asymptotic solutions to some exact solutions that came out at about the same time from this paper down below, it actually compares really nicely. But the most interesting part, so the amplitude is good and gets better as things decay, but it's really good at picking out these resonant points, which are 1 on n squared. Anti-resonant points is what they're called, which is where those are cancelling out. And if you actually look at the computed value versus the predictions, Things line up really nicely. I showed Doug this at a conference and he was really annoyed he hadn't spotted it. So thanks, Doug. Okay, so that's fine, but the total lattice is not that realistic. Let's start trying things that are a bit more realistic. Fermi past Singu is a slightly more realistic version, not perfect, but the problem is now we can't write down a leading order solution. We're kind of out of luck. But actually the reason that this particular particle chain became important is because if you have a solitary wave that's much longer than the particle distance, you can regularize it and a KdV equation falls out. And the KdV equation has soliton solutions, so maybe instead of writing down the exact leading order, we can approximate it as a KdV soliton. So now we're starting to layer approximations on each other. And both of these approximations are singular, by the way. Sorry, both of these perturbations. The mass ratio is a singular perturbation and discretization is a singular perturbation. But fortunately, it turns out it's a friendly singular perturbation, so it's not such an issue. So there's two small parameters, the long wave parameter, which is a measure of how much longer the soliton is than the particle distance, and the mass ratio. So we're going to say, look, ignore the challenging part and just say, yep, the leading order is that tanh. And then we cross our fingers and we hope it works. The leading order has singularities in the complex plane. We can calculate the singulant. We won't get such a nice value this time around. Y naught is that tanh thing, but it seems to work. The dips are about where the oscillations vanish, and we can kind of check the anti-resonance conditions, and these are pretty big values. We can compute the anti-resonance conditions, and as K increases, it gets more accurate, which is what we would expect. So even though we're starting to layer approximations on top of each other, things are still working. Buoyed by this, we're going to actually try a system we can build in a laboratory. So the Hertzian chain is this. It's what happens when you have particles that are physically in contact with each other and that push against each other, and that pushing is what transmits energy. So Guo talked a bit about this in her Newton Institute discussion, so that should be available online soon if you want to recap some of that. I want to talk a bit about what this interaction is, this delta minus r to the power of alpha with a plus at the bottom. If they are not touching each other, they are not transmitting energy no matter what's happening. That plus says that this is only non-zero if the thing inside the square brackets is positive. The physical beads touching each other tends to be represented by alpha equals 1.5. So delta is something we call the pre-compression. It's how tightly you're squeezing the chain together at the start. And we're going to say it's strong. I've just said strong. What I mean is sufficiently large such that the thing in the square brackets is never negative, and we don't have to deal with this discontinuous potential issue, which is a whole other thing. This tells us that a linear limit, which is a KdV limit, exists. So we've got strong pre-compression, so we don't have to deal with that nonsense. So what happens if we try and do the same thing? Well, I've got good news and I've got bad news. The good news is that we can predict the amplitude really well. The bad news is we completely miss anti-resonant points. We completely miss points where the contributions fail. And this is actually, if you do a lot of different systems, something that's quite common. Part of the problem is that the analytic continuation seems to be going wrong away from the real axis, which makes sense because analytic continuation is ill-posed. You can make tiny changes on the real axis and huge changes will happen out in the complex plane. So we're kind of running into the limitation of what this approximation method can do. It's still doing well. It's picking out some of them. It's not picking out all of them. Frankly, I can come up with some systems where it works a heck of a lot worse. But it would be really nice if we could kind of avoid this issue. So, okay, no worries. Well, look, that's a problem and we'll get to it, but let's try something else. And I want to try one last problem. So this is kind of the wrap up. Well, we've been using these long wave approximations, but what if we just get a whole lot more laissez-faire with what we use to approximate the system? So I'm going to try something that is kind of like a diatomic chain, except not. So this is a woodpile chain, just because life is getting hard and we want to keep things simple, where instead of being a part of the chain, our light particle is attached to the main beads by a spring response. So the Zn equation is a spring response situation. This is called a woodpile chain. It's very strongly studied both in experiment and in theory. Guo talked a lot about what it means in her discussion, and if I'll just refer you to that for more details. We're actually going to look at the zero precompression case. So we're going to set lambda equals 0. Now this has no long wave limit. This is, KdV is out of the picture. Even if we wanted to do a KdV type thing, this is a strongly nonlinear regime, and we can't lean on that anymore. There's no weakly nonlinear option. Instead, we just say, well, what if the answer looks like Tanch? Well, I didn't come up with that idea. Sen and Mansfield proposed that in 2001, and they said, well, try this. Fit C1, C3, C5, see how it works. So now we're going from, here is kind of an approximation driven by the dynamics in some sense, to an approximation because it seems like a good idea. And it is a good idea, so that's nice. Alpha is 1.5, it gets a bit funky for reasons that we sort of talk about in the paper, but as alpha increases, things get pretty good. This is surprisingly good, far better than it has any right to be, especially as alpha becomes large. But the woodpile is much friendlier than the diatomic system. And in fact, it completely misses a lot of the anti-resonance points for the diatomic problem. It does pick out the amplitude very well. Even for the diatomic problem, this is a very good way to get the amplitude of your waves. It just can't find the anti-resonance points. So what's going on? Well, approximating the leading order solution can give you the appropriate Stokes curve behavior, but there's a lot going on that you're not seeing, and maybe I need to be a bit more thoughtful about. It's not such a problem for the amplitude, which depends only on a single contribution, but it is much, much more important for things like anti-resonance conditions, because that's the interaction between contributions. And given that our waves are very short, they have wavelength epsilon, even tiny, tiny errors in the analytic continuation are going to cause problems. Now, sometimes you get lucky and things work. We just saw that. These pictures weren't terrible, but we'd like to be able to do better. A lot of thought and a lot of discussion has kind of led me to the idea, and this is where I'm essentially going to leave it, is we need to come up with an analytic continuation that preserves the singularity strength and position as well as the global behavior. So what I've got down the bottom is a part A approximate type approximation. So the exact solution on the left has a branch cut at 0, order, I can't remember, a half, I guess, but rotated. No, 3 on 2. Whereas the one on the right, and what you tend to see with these rational approximation situations, is this accumulation of simple poles. So away from the poles, everything looks right. But in the neighborhood of the poles, it can tell you the position. You can see where it's accumulating, which is at 0, but the order is wrong. So if you want a really robust method, we need to think about how we're numerically approximating our analytic continuation. And we're working on that. There's a few of us who have started tackling this problem, and I think it's really promising in terms of making this a quite accessible set of methods for applied mathematicians who maybe aren't interested or have problems that are too complicated to solve exactly, which, to be fair, is most of them. Okay, so I asked 4 questions at the start, and over the course of the last, I haven't looked at a clock since I started talking. I answered them all, so let's just quickly recap. Do submarines create a Kelvin wedge? They absolutely do, except it's a little more subtle than ships because there's these kind of hierarchy of Stokes switching. What is the role played by higher order Stokes curves in unsteady flow? They actually tell us which wave regions are viable and which ones don't really exist, even though Stokes phenomenon taken naively would indicate otherwise. If you don't include it, you get the wrong answer. Granular chains, what causes anti-resonance conditions? Stokes contributions that cancel each other out. And finally, what happens when we can't even obtain exact leading order solutions? You can approximate the leading order sometimes, question mark. We haven't quite figured out all the details on that, but it seems like it can work if we're careful. All right, that's basically all I had to say. I drew from a lot of papers for that talk, so here's the biography. Feel free to pause, look at the video and pause it if you want to check those out. I also, a lot of papers, a lot of collaborators and people I talked to, John, Ravi, Lyndon, Scott, Tim, Phil, Shane, Steve, Guo, Mason, Aaron, Nalini, and Doug, all contributed either as a co-author or someone whose discussion I valued greatly over the course of these projects. I was funded by an ARC Discovery project. Thank you very much to the Isaac Newton Institute for this whole program. And thank you for all of the organizers. And if that seems self-indulgent, you can mentally append "except Chris" at the end. Thank you very much. I really enjoyed giving that talk.
Okay, thank you very much, Chris. That was a really interesting talk. Does anybody have any questions?
I have a question.
Yes, go ahead.
Towards the end of the first part of your talk, you indicated that you'd had a brief encounter with elliptic curves, but it hadn't been consummated. Did you somehow need to take the square root of a quartic?
Yeah, there was a lot going on. This is really nice, like the equations, because I'm essentially equating, when you're finding these, I just hit page up way too many times. All right, so when you're finding these curves, remember you're equating two different Stokes, two different singulants. And that's quite complicated, and you're essentially solving where they equal 0. You should probably, I should probably just do it numerically, but basically it's this condition here, which is where these come from. So there's no square rooting, I guess. But either way, I didn't delve into any real theory on that. I just plotted curves in Mathematica a lot and then looked at what was going on a lot. And this picture was the picture that summarized it all, but I cannot stress enough, I did not get there easily. There's 4 dimensions to be playing in here, right? There's real x, imaginary x, real y, imaginary y. And trying to kind of figure out which curves connect to what. It's a super interesting problem, but it's very difficult. And this is why, you know, for example, in Yannis's discussion where he's doing these internal waves, he has to include Z as well. Eventually you run into this curse of dimensionality where it's really hard to see how all of these Stokes curves interact unless you can somehow manage to convince your brain to see in 5 dimensions. Lots of paper, lots of string, looking like a crazy person. Fun though. John has his hand up.
Yeah.
I do indeed. 2 questions if I'm allowed. So the second part, is there any mileage in putting alpha as 1 plus epsilon or 1 over epsilon?
Yeah. I apologize. I had some slight tech issues that meant I missed that question. Could you say it again?
Yeah, so second half, have you tried putting alpha as 1 plus epsilon or 1 over epsilon?
I haven't. Someone suggested that in Guo's discussion. Was it you? No, Phil suggested it, and we noted it down because there is absolutely mileage in doing that, and we haven't done it yet. I'd like to. It'd be interesting. We're gonna give it a go.
Ryan, a general question on the first part, which isn't terribly profound, but you linearize and then you start expanding. Are there interesting problems where that's a dangerous thing to do? The limits don't commute.
I've not found one in a water wave context. I don't know. The nonlinear water wave problem is super interesting, but so I tried sort of what happens if delta is like epsilon to the power of something. You can kind of force it into the equations if you balance them right. But I couldn't, it seemed algebraically interesting without being physically so meaningful. In a sense that I guess what is a linearized system that meaningful? I couldn't really justify it other than my own interest. because you can pick a delta that is proportional to epsilon, and you start to pick up terms further down. But I don't know, I never found anything super interesting falling out of that.
Thank you, Chris.
But it's also been a very long time, and I am a bit more grown up now, and maybe I should try again just to see. John, you should remember this.
Hey.
Oh, you assessed it.
Oh yes, I've forgotten that, but that was a long time ago.
Yeah.
Did you pass?
I mean, with minor corrections.
Okay, any other questions? I have one. So the origin of the Tanch expansions, I mean, is that coming from a resummation of a trend series?
Do you mean in the Senemantiu Tanch?
Yeah, well, in wherever you get the Tanch, I mean, it was a bit of a rabbit out of a hat. So, for example, there, yeah, I mean.
Yeah. No, nothing so sophisticated. It was a guessed ansatz. It was an observation that solitary waves in granular systems that they can solve are often Tanch.
Okay.
KDV is Tanch. But there's nothing. This is one of the things that I'd actually sort of like to kind of reappraise, because I think the right approach is kind of a multiple scales type, not multiple scales, well-ish, to rather than using the Tanch to force the behavior to be right, using like a rational approximation, which should hopefully sort of not do that forcing. But if you know the answer is going to be Tanch-ish, then it's no less valid than a rational approximation. But maybe using a different local expansion within the neighborhood of those poles to preserve the actual correct singularity strength rather than the fake one.
But I mean, one way might be to just try a trans series ansatz and just to see whether the resummation just gives you the Tanch or whether it doesn't give you something slightly different that
would be interesting.
That might address that. I don't know. But anyway.
Yeah, I mean, part of the problem is that at some point you have to solve something, and you kind of can't. There's sort of too much going on to write down a solution, and a trans series probably gives you a lot of equations that you can't solve rather than one equation that you can't solve. But at some point, if you want to do better than approximation, you have to be able to write down an answer.
Okay.
And that's where we run into trouble. Well, not trouble. That's where we expose new and interesting vistas.
And we, yes. Okay. Any other questions for Chris? Okay, so I think we can stop the recording.